In the previous video, we learned how to name unbranched alkanes and how to name substituents. And we did each of those individually. Now we're going to put all of that together and name alkanes that contain substituents. And we call this the IUPAC system. So this is just the systematic way of naming all of these molecules. The first thing we're going to do is find the longest continuous carbon chain on the molecule. And that longest continuous carbon chain is going to be called the parent. That will be the parent name of that particular molecule. So I'm going to copy this and I'll look at a couple of different options for finding the longest chain. I could go directly across, in which case I see that there are 5 carbons in that chain, or I could start up top and continue down to the right, and there are still 5 carbons in the chain. So in this scenario, it really doesn't matter which option I choose. The longest continuous chain will be 5 carbons long, which means that the parent in this case is pentane. Pent telling me that there are 5 carbons in the molecule, and ane telling me that it's an alkane because all of these carbons and hydrogens, everything has single bonds. The second thing will be to number the carbons starting from the carbon closest to the first branch. And really what this is saying is that our ultimate goal is to give the branches the lowest possible number. And I do want to remind you and emphasize that here I'm using the term branch and the term substituent interchangeably because they really mean the same thing. So when I say substituent or branch, I'm referring to this little carbon that's sticking off of that main parent chain. All right, I'm going to copy my molecule and I'll try a couple of different options. Okay, I want to start numbering, actually I'll try 3 options. I want to start numbering on the side that is closest to the branch. So I could go in this direction, or I could start up top and go in this direction. And you will see that whether you started on the top or on the left, it will end up generating the exact same name. So either option is valid. What you don't want to do in this scenario is to start from right to left, because notice, if I go left to right, the first substituent appears on carbon 2. Same thing here, first substituent appears on carbon 2. But if I look on the right to left version, the first substituent appears on carbon 4, and that is not what I want. I want to give the substituent the lowest possible number. So either the left or the middle version would be fine. You don't want to use the version on the right. The third thing I will do is name the substituents. In this case, we only have 1, but in most scenarios, you will have more than 1. And we do need to indicate where those substituents appear. So we're going to indicate numerically on which carbon they appear. So you're going to give your substituent an address. You're going to say, where does this thing live? Where is it located? And we're going to use dashes, or in this case, 1 dash, because we have 1 substituent, to separate the carbon number and the substituent name. So in our previous example, I'm just going to move this down a little bit. Okay. I see that this substituent has 1 carbon, and the prefix for 1 was meth, so it gets the prefix meth. I will give it the ending YL, which tells me that this is a substituent, right? It's hanging off of that primary chain. And it appears on carbon 2. That's the carbon it's attached to. So I'm going to call it 2-methyl. So meth tells me 1 carbon. YL tells me that it's a substituent. And 2 is telling me the carbon it is attached to. And notice on the system in the middle, if we use that numbering system, it would end up generating the exact same thing. This substituent contains 1 carbon. It's attached to carbon 2, so we would call it 2-methyl. Okay, now that we have that, we're going to put everything together into the full name of this molecule. And we're going to list the substituents first. And the parent name is always last. And I will say we'll list the substituents first. They will be in alphabetical order, which in this scenario doesn't matter because there's only one substituent, but we'll take a look at more interesting examples after. So in that molecule we said that the parent name was pentane because the main chain had 5 carbons. And we said the substituent was 2-methyl. And we're just going to put that together. So I'm going to call that 2-methyl pentane. And that just becomes one word. It all gets squished together into one word. Okay, so in this case, we only had one substituent, but most of the time the molecules will be larger and there will be multiples. So sometimes you'll run into a scenario where you have 2 or more of the same substituent. So in this case, if I had multiple methyl groups on a molecule, if that happens, then we're going to use prefixes to indicate how many of them appear on that particular molecule. If we have 2 of them, then the prefix will be di. If 3 of them, the prefix will be tri. 4 will be tetra. 5 penta. 6 hexa, and so on and so forth. In reality, you will probably rarely see the penta and hexa because the molecules would have to get really large in order for that to happen. But di, tri, and tetra do occur fairly frequently. So let's take a look at an example of that. Okay, very similar to the molecule we just worked with, but there's one extra carbon here. So notice I can still continue directly across to find the longest continuous carbon chain. And in this scenario, the parent is still pentane. The longest continuous carbon chain has 5 carbons. It's an alkane, so I'm going to call it pentane. And then I'm going to take this molecule and I'm going to number it. And actually I can number directly. So I can go 1, 2, 3, 4, 5. Notice that in this case, it really doesn't matter which direction I number in. So I could have alternatively gone right to left. And in either case, the substituents appear on carbon 2 and carbon 4. So in this case, because the molecule is symmetric, it doesn't matter which version of numbering you do, you'll end up generating the exact same name. So that's kind of nice, pretty convenient there. Okay, I see that this substituent has 1 carbon, so the prefix is meth, and I'll give it that ending YL to indicate that it's an alkyl group. And it appears on carbon 2, so I'm going to call that 2-methyl. But this substituent is also a methyl group. It also has one carbon, but it appears on carbon 4, so I'll call it 4-methyl. Since I have two of the same substituent, I'm going to use the prefix di to indicate that there are two methyl groups. So this will turn into dimethyl. However, I do have to indicate where these methyl groups appear because they're on carbons 2 and 4, but that doesn't necessarily have to be the case. What if I had methyl groups on carbons 2 and 3? Right, so I do need to have some way of distinguishing where these carbons appear. So I'm going to indicate numerically where each substituent appears, separating the carbon numbers by commas. Okay, so they appear on carbons 2 and 4. I'm separating those numbers by commas. Then I will use a dash and say dimethyl. So same system as before. And then I'll tack on the parent name, which is pentane. So this molecule ends up being called 2,4-dimethyl pentane. Okay, let's try another example just to practice this. Okay. Feel free to pause this video and try to do this on your own, and then you can take a look at the solution. All right, I see that the longest continuous carbon chain is still 5 carbons. So the parent here will be pentane. And I'm going to number that left to right because that will give both of my substituents here the lowest possible number. And I see that each substituent has one carbon. They're both methyl groups, which means I'm going to call them dimethyl, di indicating that there are two of them. So meth is telling me one carbon, YL is telling me that they are substituents, and di is saying that there are two of those substituents. But now I have to indicate where they both appear. And you do want to include the numbers of both of them because they both appear on carbon 2. So in the previous example, we had 2 methyl groups and notice that they were on different carbons. So even if they're attached to the same carbon, you do want to indicate that numbering. So I'm going to call this full molecule 2,2-dimethyl pentane. So just like the previous examples, the parent name comes at the end and it all gets compressed together into one name. Okay, so in all of these examples, we saw scenarios where it's all the same substituent, but you could have different substituents, in which case you will list the substituents in alphabetical order. Separated by dashes. Followed by the parent name. And notice that the parent name never has a dash in front of it. It just gets attached at the very end. Let's try an example. And I'll try a couple of different numbering systems and see where to go from there. So I'll try right to left and left to right and kind of see how it goes. Okay. So I see that in either case, the longest chain is 6 carbons long. So the parent name will be hexane. Hex indicating that there are 6 carbons, ane indicating that it's an alkane. Now notice on the numbering system on the left, the substituents appear on carbons 3 and 5. On the example on the right, the substituents appear on carbons 2 and 4. So this is the numbering system I want to use. I want to give them the lowest possible number. I do not want to give them higher numbers than I have to. Okay, and if you recall from the previous videos, when we had halogens as substituents, we changed the I and E ending to O. So we have a fluoro that appears on carbon 2. So I'm going to call that 2-fluoro. And then I have a bromo that appears on carbon 4. And I will call that 4-bromo. And now I have to decide, okay, well, same sort of system. I'm going to list the substituents, then the parent name at the end. But I have to decide which substituent will go first. And here I want to use alphabetical order, not numerical order. And well, B comes before F in the alphabet, so bromo will be listed before fluoro. And that full name will become 4-bromo, 2-fluoro, hexane. So go by alphabetical order when you're listing the substituents, not by numerical order, because notice that 4-bromo numerically comes after fluoro, but that doesn't matter when we're naming it. We want to make sure that they're listed in alphabetical order. Now, if you think back to the previous examples where we had these prefixes di, so you could be di, tri, tetra, etc. We now have to think about, well, how are we going to alphabetize if we have multiple substituents and they have those prefixes? And when it comes to alphabetical order, iso is the only prefix that is considered when alphabetizing. Now, the substituents are the prefixes of the substituents are always listed in the name, but they're not considered when alphabetizing unless it's iso. So the following prefixes are ignored when alphabetizing. You will list them, but you will not alphabetize according to them. So di, tri, tetra, penta, anything indicating how many of the same substituent you will not consider when alphabetizing. Also sec and tert. So if you think back to sec-butyl, tert-butyl, these prefixes you would not consider when alphabetizing. Let's take a look at an example of this sort of scenario. Okay, I have a molecule. I'm going to try a couple of different numbering systems. So I could go left to right or right to left, just like I've been doing before. Notice that I could have started numbering down here instead, and I would end up generating the exact same chain length. So whether you started on the left or you started on the bottom and went to the right, it would be fine. Okay, so in the example on the left, I see that my substituents will appear on carbons 3 and 5. In the example on the right, the substituents appear on carbons 2 and 4. And I want to give the substituents the lowest possible number, so I'm going to use the system on the left, not the system on the right. And in this scenario, I see that the longest continuous carbon chain is 6 carbons long. So the parent here is hexane. And then I'm going to take a look at these substituents individually. I see that there are 2 methyl groups on carbon 2, so I'm going to call those 2,2-dimethyl. And then on carbon 4, we have a substituent that contains 2 carbons. So I'll indicate 4, saying that it's attached to carbon 4. But because it has 2 carbons, the prefix will be eth, and then it still gets that YL ending to indicate that it's a branch. So that becomes 4-ethyl. Now I have to put these substituents into alphabetical order, and keep in mind that di is not considered when alphabetizing. So I'm actually going to alphabetize by M, not D, which means that I have a substituent starting with E, and then a substituent, I can say, starting with M. So ethyl will actually be listed first. And that full name will become 4-ethyl 2,2-dimethyl hexane. And that's the full name of this molecule. Okay, there are just a few more things we need to mention for some strange scenarios you might encounter. So sometimes you will have a case, and I'll show you an example, and then I'll write out some guidelines for handling this. So here I have a molecule. I'm going to try numbering it in 2 different ways. So I could go left to right. I could go right to left. Notice that in either case, my substituents appear on carbons 2 and 4. Now, if these substituents were the same, then I would say, okay, cool, doesn't matter. I could choose either direction, no problem. But these are not the same substituent. I have a methyl group right here, and then I have a bromo. So I have to decide which substituent am I going to prioritize in this scenario. So if you need to break a tie between 2 equally ranking substituents when numbering the parent chain, then you will go by alphabetical order of the substituents. And the key here is equally ranking. Keep in mind that halogens and alkyl groups have the same naming priority. So neither of them is more important than the other. They are equally ranking. So the only way for me to break the tie here is using alphabetical order. Eventually, we're going to discuss different functional groups, and in that case, you will see some higher ranked functional groups, and then that system will change. But for now, they're all exactly equal. So now I have to decide, okay, well, bromo starts with B, methyl starts with M, which means that bromo is going to have the higher priority due to its alphabetical order. So I'm actually going to choose this version, not this version. I want to give the one that comes first alphabetically the lowest possible number. And I'll just copy this over to the next page, and let's name that full molecule while we're at it. All right, I see the parent chain here will be pentane because it contains 5 carbons. I see that there is a 2-bromo. So bromo, it appears on carbon 2. And then there is a 4-methyl substituent. Bromo comes first alphabetically, so I will list it first, and then methyl. And then I'll attach the parent name at the very end. And this becomes 2-bromo, 4-methyl pentane. couple more things I would like to mention. So one thing to watch out for, caution, the longest continuous carbon chain is not always directly across. In all the examples we looked at thus far, we saw, okay, well, if I just go directly across, cool, it's the longest continuous carbon chain. I don't really have to think about it. But that's not always that straightforward. For example, ooh, those are some funky bond angles right there. Okay, so if I go directly across, just like I have been doing, it looks like I have 6 carbons in my longest continuous carbon chain. But if I actually start up top or on the right and continue all the way down this way, then there are 7 carbons in the longest continuous carbon chain. And then the parent would be heptane. So I want the longest continuous carbon chain possible, which means in this scenario, I'm going to go with this version, not with the version on the left. So just watch out for that when you're naming molecules. Sometimes these bonds are rotated in strange ways, and there is a longer version that isn't just directly left to right. Another thing to watch out for, and this rarely comes up, but there are scenarios where it does, so let's be prepared for that. If there are 2 paths that have the same length, so same number of carbons, choose the one with most branching. Let's look at an example of that. Okay, I'll try a couple of different options here. All right, I could go directly across, and in that scenario, this longest continuous chain has 6 carbons. Cool. Or I could go in this direction and the longest continuous carbon chain still has 6 carbons. And then I have to decide, well, which version do I want to prioritize? In the version on the left, it looks like I have 1 substituent. I would have an isopropyl group there. And I'll just highlight that in a different color. In the version on the right, I have 2 substituents. I would have a methyl group and an ethyl group. And I want the version that has most branching. So this is the version that I would want, not the one on the left.